This is our first video on logarithmic functions, and by the end of this lesson you'll be able to do several things. You'll be able to define a logarithmic function, evaluate logarithmic expressions, graph a logarithmic function, explore the inverse relationship between exponential and logarithmic functions, and apply logarithmic functions to real-life situations. So, as you're going through this, you should be thinking about how logarithmic functions model real-world problems and their solutions, how we can graph logarithmic functions, and again, what effects h and k have on those graphs, and how we can simplify and evaluate logarithmic expressions without the use of a calculator. A new vocabulary will be a logarithm, and then we'll talk about what a common logarithm and a natural logarithm are. And this video will be in 3 parts. The first part will be an introduction and simplifying, and then graphing, and then applications. So first of all, let's talk about what a logarithm is. So we know, for example, that 2 squared is 4 and 2 cubed is 8. But for what value of x does 2 to the x power equal 6? So we can expect that it's somewhere between 2 and 3, just from, well, what you know and this information up here. But how do we know exactly what the value is? And this is why we have logarithms. We will talk about specifically how to solve this problem later. So in general, we say that b and y are positive numbers and b is not 1. The logarithm of y with base b is written as this, log sub b with a y. And it's read as log base b of y. And we know that log base b of y is equal to x if and only if b to the x power is equal to y. And this is what you should be thinking as we go through these examples. This is the form you're used to. B to the x power equals y. This tells us that these two equations, log of b, log base b of y is x and b to the x power is y, are equivalent. We call this first one logarithmic form and the second one exponential, which you're already familiar with. But this means if we have an equation in one of those forms, we can always rewrite it in the other, and that's what we're going to practice now. So, how I always start this is I make sure I have my kind of generic forms written near where my practice problems are, because this helps me with my setup. You don't have to do this, but I would write out actually that log base b of y equals x, and then on this exponential side I would write b to the x power equals y. So if I start out with a logarithmic form of b base 2, y 32, and x is 5, I could rewrite that so my base was 2, my x was 5, and my y was 32. So in exponential form, that would be 2 to the 5th power is 32. Let's take it back the other way. If it helps to label these at the beginning, definitely do that. So 5 is b, my 0 is x, and my 1 is y. So if I want to write that in logarithmic form, I would say log. My base is 5, my y is 1, and that's equal to my x value of 0. So log 10 of 10 is equal to 1. That would be 10 to the first power is equal to 10. And then going back the other way, this would be log base 10. 1/10 is equal to -1. And finally, I would have 1/2 to the negative first power is equal to 2. And a couple of special notes here. You should recognize that log base b of 1 is equal to 0 because b to the 0 power is 1. And log base b of b is 1 because b to the first power is b. Next, we'll look at evaluating some logarithmic expressions. So when we're trying to find the value of any log base b of y, the question we are asking ourselves is what power of b gives you y? And again, I'm just going to write out that generic function of log base b of y is equal to x because that helps me in my setup. So for example, if I was evaluating log base 3, 81, how I could rewrite that would be to say 3 to the x power is 81. And so in this question, what power of b gives you y? We're saying what power of 3 gives us 81? And 3 to the 4th power is 81, so x is equal to 4. This one might be a little bit less straightforward, but it's the same question. What power of b, 1/2, gives us y, or 8? 1/2 to the negative 3rd power is equal to 8. And finally, we would be saying what power of 9 gives us 3? And 9 to the 1/2 power is equal to 3. A couple of new vocabulary terms. The common logarithm is a logarithm with base 10. You might see this written as log base 10, but usually you'll just see it written as log. And similarly, a natural logarithm is a logarithm with base e. And so you might see it written as log base e, but usually you will see this abbreviation ln, and ln means natural log. Now on your calculators, you can only evaluate with the log and natural log buttons. Those are just for base 10 or log e. So these examples that we did at the top, you need to be able to do without the use of a calculator. Soon we'll talk about change of base formula, but for now you should be brushing up on your exponents, and especially when they involve a fractional exponent or a negative number. Back to that example with the table though, I want to highlight a couple of things. These two. You would not normally see that written with the base 10 in there. Both of those would just say log. So log 10 equals 1. Log 1/10 equals -1. And I'm actually going to make this the end of part 1, and that stuff that was on using inverse properties, I'm going to bump that over to part 2 because I've already been talking for about 9 minutes. So you can stop here for today and then add the inverse properties to graphing for part 2. All right, next we will talk about using these inverse properties. So logarithms are the inverse of exponential functions, or they undo each other. So this means a couple of things. So first of all, g of f of x, or log base b of b, is equal to x. Because this would just be saying b to the x power is b. And f of g of x, or b to the log b of x power is also equal to x. So let's see how that actually applies to a couple of real examples. So this first one, 10 to the log 4 power. When you just see the log written like that, it's a common logarithm, or base 10. So if it's helpful, I could rewrite that as 10 log base 10 4. And this looks just like this example here. And so using inverse properties, this would just be equal to 4. Sometimes you're going to have to do a little bit more work, and this should kind of be a throwback to Algebra 1, where we can rewrite to use the same base. And in this case, I can rewrite both of these as a power of 3. So if I want to use these inverse properties, I need something that looks like one of these, and I don't have that yet. But what I can do is I can rewrite this as log base 3, and instead of 9, I'm going to write 2 squared, and I still have this x. And then I can rewrite that as log base 3, 3 to the 2x power. And now I'm able to simplify, and this would just be equal to 2x. Now let's take it a step further and actually find the inverse. In this first example, find the inverse of y is equal to log base 2 of x. Now this is just the definition of a logarithm and exponential function being inverse of each other. This is just a basic logarithm, so it would be the inverse of this function y is equal to the 2 to the x power. The second one is a little bit less straightforward. Think back to when we were talking about quadratic equations, and we were looking for the inverse of a quadratic graph, or any graph really. And if you remember, what we did was we switched x and y. So instead of y is equal to this, I had x is equal to natural log y plus 4, and then we solved for y. And next I want to take this natural logarithm and write it in exponential form. And so the inverse of these natural log functions are e functions. So I could say e to the x power is equal to y plus 4. And the reason that I can say that is that e and natural log are inverse operations, or they undo each other, so they would cancel each other out. Now I'm left with e to the x power is equal to y plus 4, and the last thing that I need to do is just subtract 4 from each side. So I'm left with e to the x power minus 4 is y, and that would be the inverse of that function. And what we will do next is look at some graphing examples. So again, we have to really remember that a logarithmic function is the inverse of an exponential function. So what does that mean for graphing? So let's take just a basic log function of any base b, and then I have an h and a k. The line x is equal to h is going to be our vertical asymptote. Now that makes sense because when we graphed exponential functions, we had a horizontal asymptote. So we had an asymptote of y is equal to something, and it was a line straight across that the graph was going to, remember, approach but not touch. Now in this case for log functions, it's a vertical asymptote. The domain is going to be x is greater than h, and the range is all real numbers. So if you remember with exponential functions, the domain was all real numbers, and the range would change depending on what our k value was. This time, because h will shift our graph left and right, that will impact the domain. So the domain is going to be any value x is greater than h, and the range will always be all real numbers. Now, if b is greater than 1, the graph moves up to the right. If b is between 0 and 1, the graph moves down to the right. Just like we did with these transformations of exponential functions, we can graph the parent function first and then move those points around for h and for k. Now, I'm talking about logarithmic functions. So in this first example, y is equal to log base 1/2 of x plus 2. What I will start off by doing is just coming up with some values that I can use. And so I want to write out this form. What I'm saying is 1/2 to some power is equal to x. So my input x is going to give me some power of 1/2 that I'll use as my y value. So let's start out with something pretty straightforward, which would be 1/2 to some power equals 1. And anything to the 0 power is 1. So 1/2 to the 0 power is 1. And I put in 1 and I got out 0. Now this makes sense because when we did exponential functions, the y-intercept was 0, 1. So now it makes sense that if this is the inverse, the x-intercept is going to be 1, 0. So I'm going to plot that point 1, 0. And until you get used to what these graphs look like, I would do a couple more numbers. Now, I'm talking about a fraction raised to some power, and I really don't want to have that x value keep getting smaller and smaller and smaller, because then it makes it tough to plot and really see what it's doing. We want to see a trend going down this way. So let's do 1/2 to some power is 2. And 1/2 to the negative first power is 2. So another point on this graph is going to be 2, -1. And just do another point until you really get used to what these look like. So another point that I could do here is 1/2 to the negative second power is 4. So another point on my graph is 4, -2. So my graph is going to go this way, and it will curve up this way to my vertical asymptote of y is equal to 0. Or I'm sorry, x is equal to 0. And if you needed some help seeing how that was going to work, what you could definitely do is plug in some positive values for power of 1/2. So for example, 1/2 squared is equal to an x value of 1/4. So if I put in 1/4, I get out 2. Or similarly, I could say 1/2 to the third power is equal to 1/8. So if I put in 1/8, I get out 3. So here you can see this pattern that's starting to form, and that's my x values are getting smaller and smaller and smaller. My y values are just going to keep going up because that is my vertical asymptote. So I would have this point of 1/4 and 2 and 1/8 and 3. And I'm approaching that y-axis, but it's never actually going to hit the y-axis. But the last thing that I need to do with this graph is I have that k value of +2. So I'm going to switch colors on the pen, and I need to move those points that I plotted up 2. And then I had this one. And so this is roughly what, except it shouldn't be touching the y-axis there. This is roughly what that graph should look like. So my range is always all real numbers. So my range is all real numbers. And in this case, my domain is anything greater than 0 where that vertical asymptote is. So domain is anything for x is greater than 0. Alright, so we will go through that second example as well. And second example that we are looking at is y is equal to log of 6 times x minus 3. And I want to start out the same way. I'm going to graph that parent function first, and then that -3 is an h value, and it means I'm going to shift the whole thing 3 to the right. So I want to start out by getting some points. So here it's going to be 6 to some power is equal to whatever I put in for x. So let's start out with our intercept again. It should still be 1, 0, but let's check it. If I put in 1 for x, 6 to the 0 power is equal to 1. So I have a point at 1, 0. This one's a bit easier. It doesn't involve a fraction. So another easy point to get would be 6 to the first power is 6. But remember, it's not 1, 6 because 6 is our x value. It's what we're actually putting into the function. So I should have a point at 6, 1. So we'll do this first line in red, and I have a point at 1, 0, and I have a point at 6, 1. So this graph is going to go up this way, and my vertical asymptote will go down. Now again, if this didn't make sense to you how to finish drawing the graph, you can try to come up with one more point that will kind of indicate the direction that the bottom part of this graph is going. So for example, 6 to some power, let's do, is 1/6. And that would be 6 to the negative first power, which means if I put 1/6 in, I get -1 out. So that 0.16 -1 would be right about there on my graph. Now though, I need to shift that entire graph 3 places to the right. So I'll take those 2 points that I plotted and I will move them 3 places to the right. And now my domain will be for anything where x is greater than that h value of 3. So x is greater than 3. And my range is still all real numbers. And I have that vertical asymptote at 3. And this is the end of part 2, so the last thing that we need to look at is just a couple of applications of logarithmic functions. And we have looked at a couple of examples in exponential growth and decay where we were just solving for a time in years or whatever this power was raised to and representing in this equation. However, now we're going to look at that, but also solving for a variable other than time. And this should kind of be a throwback to your Algebra 1 class. So very first thing is, let's look at this equation. In a bacterial culture, the number B of bacteria is modeled by the equation B is equal to 12,000 times E raised to the 2700ths times T power, and T represents the number of hours since noon. We're going to look at two questions. One, how many bacteria to the nearest whole number will be present at 7 o'clock p.m.? This one is very straightforward, and this is just like the examples you were doing with exponential growth and decay. It's really just plug in a value, run it through your calculator, get an answer. Part B is a little bit trickier, and we'll go through that one step by step. How many hours, correct to 3 decimal places, will it take for there to be 180,000 bacteria? So in that case, we're going to be solving for T. But let's do part A first. So how many bacteria to the nearest whole number will be present at 7 p.m.? So this is 7 p.m. would be 7 hours after our start time of noon. So in our equation, we would say B is equal to 12,000 times E raised to the 0.27 times 7th power. And if we run all that math through our calculator, we get 79,432 bacteria. This second example, how many hours will it take for there to be 180,000 bacteria? Let's fill in what we know first and go from there. So 180,000 is equal to 12,000, same first equation, times e to the 2700ths times h power. And we're trying to figure out what h would be. The very first thing that I can do here, though, is I can divide each side by 12,000, and that will simplify what we're working with a little bit. So what I have left with on the left-hand side is 15, and here I have e to the 2700ths times h power. Now I need to use this idea of e, the natural base, and the natural log, ln, being inverse functions. And how I can simplify this is to take the natural log of each side. Now, on the left-hand side, this would leave me with the natural log of 15. And on the right-hand side, it would leave me with the natural log times e raised to the 2700ths times h, or t, power. When I do this, these will cancel each other out. And so what I'm left with is something that I can actually solve. And that's natural log of 15 is equal to the 0.27 times h. And to finish this, I just need to divide each side by 2700ths. And those simplify. They cancel each other out. And I end up with 10.030 hours. My recommendation, especially as you just start to do these, to make sure that you're correct, is to really just go back and check this. So run this through your equation by putting it in as the value for t and making sure you get about 180,000. You won't get exactly that because you rounded, but you should get very, very close to 180,000. I think when I checked this, it was about 180,008. So that's how you know you got the right answer. The very last thing that I want to look at is how we can apply this idea of simplifying by inverse functions to a problem where it's not an easy whole number solution. So log base 16 of 8. What I want to know is 16 to the sum power of x is equal to 8. Now, that's not really obvious as we just look at that, what that answer would be. What we can do, though, is we can rewrite each of those as a power of 2. So 16 would be 2 to the 4th power times x, and 8 would be 2 to the 3rd power. And I have a common base here. So I can simplify that to 4x is equal to 3. divide each side by 4, and I have x is equal to 3/4. And the last thing I want to point out is that this strategy would have worked back on this problem where it was a little more doable in your head, but I just want to show you. If we were looking at this problem, log base 9 of 3, and I still have this 9 to some x power is equal to 3, but I could rewrite that as 3 squared, 3 to the 2x power is equal to 3 to the first power. I have the same base, so 2x is equal to 1, divide each side by 2, and x is equal to 1/2. So you could have gotten that answer by applying that strategy if it wasn't automatically obvious to you. But that takes us through all 3 parts of logarithmic functions. So at this point, you should be able to define a logarithmic function and understand it as the inverse of an exponential function. Also, those terms of common and natural logarithms. And you should be comfortable evaluating and graphing logarithmic expressions, and also applying those expressions to real-life situations, and especially those situations where you're not necessarily just solving for the time, when you might be searching for the final number at the end. And you don't have any practice problems to do with these, but you on the video, but you do have quite a few practice problems in your guided notes.